Okay, today we are going to start a new topic, which is thermodynamics. So, thermodynamics is a general subject. It's a general subject which can be applied to any system. General subject which can be applied to any system. It is basically revolving around conservation of energy. So this subject revolves around conservation of energy. In fact, when we go to the first law of thermodynamics, we are going to see it is a statement of conservation of energy. But here in thermodynamics, we are going to look at energy conservation from a microscopic point of view also to certain level. For example, what is the energy stored by molecules of a substance? We are going to look at that to certain depth. Because when you looked at conservation of energy in mechanics, we did not really go deep into that object, inside the object, and we never looked at what is the energy possessed by the molecules of the object. But in thermodynamics, we are going to look at that. And it is in fact, you can say, generalization of the energy conservation which we discussed in mechanics. It is a higher level generalization. Okay, sometimes in mechanics you are unable to account for the energy, but that will be accounted for in thermodynamics. For example, you see, when a person is walking on a, let us say, rough surface, so the force of friction on the leg which is in contact with the ground, that is in the forward direction. So on the person the friction acts in the forward direction, we saw that, and that is of course a static friction. So on the leg friction is in forward direction, on the ground friction is in backward direction, that is okay, but on the person the friction is in forward direction. In fact, that force only is making the person's center of mass accelerate, no doubt. But if you look at this from work energy point of view, work done by friction is actually zero, because friction is acting on the foot which is at rest on the ground, so the point where friction is acting has no displacement, so work done by friction is zero. But if you see from the other perspective, kinetic energy of the person is changing, and work done by the other forces like normal contact force is zero. Work done by mg on an average is zero, because the center of mass might go up if you lift the foot and might come down when you bring the foot down. So on the whole, work done by mg is zero. So if you apply work energy theorem, you get a very strange thing. Work done by mg plus work done by friction plus work done by normal, these are the only three forces acting, should be change in kinetic energy. Work done by mg, let us say, is zero on an average on the whole. Normal acts on the foot which is at rest on the ground, so work done by normal is zero, because the displacement of the point where normal acts is zero. Friction is static, acting at a point on the foot which is at rest, so again this is zero. But kinetic energy is changing. A person at rest suddenly starts moving, so his center of mass has actually some velocity, so there is some kinetic energy. So you see work energy theorem is failing here in certain sense. The reason being, this work energy theorem statement in mechanics was derived for a particle, and this human being is not behaving as a particle, because any body which is in translation you can treat it as a particle, but the human being is not translating. One foot is at rest and other foot is moving, so it is not translatory motion really. You see, it's a very more complex motion which involves multiple translations and rotations and even more complex motions. So you can't treat the person as a particle, so you can't use work energy theorem in the form which we derived it for particles in mechanics. But in thermodynamics we have a completely different concept which is called internal energy. We'll talk about that later. So the work energy theorem will be generalized, saying that work done by all forces is change in kinetic plus change in internal energy also. Now if you include that extra term called internal energy, you can explain this. Okay, kinetic energy of the person increased because his internal energy decreased. In fact, after walking some distance, he will feel hungry because his stored energy in the body, internal energy, decreased. He used that to perform this task called walking. So this kind of analysis is actually the subject of thermodynamics. So the concept of internal energy will be dealt very thoroughly in thermodynamics. So it is a more general subject. Okay, it involves it is revolving around the principle of conservation of energy, but it is a generalization of that principle to even more complicated systems. So our thermodynamics can be applied to any system, but in our course we are going to mainly apply this subject of thermodynamics to a very specific system called an ideal gas in a container. Even though thermodynamics is applicable to every system, but we are going to apply thermodynamics to a gas, and more specifically most of the time ideal gas in a container. That is going to be our system. So we have a container and we have ideal gas in it, and there can be many more complex things like pistons, etc., where this gas can expand by moving a piston and things like that. But in general we are going to apply the subject of thermodynamics to an ideal gas in a container. That is our system. But of course you can apply thermodynamics to even more complicated systems. You can apply it to stars, thermodynamics of stars, or any system that you choose in the universe, or as universe as a whole also you can apply this subject of thermodynamics. Now before we go into this subject, there are two things that we should understand, two terms. The first term is called thermodynamic equilibrium. This is one term which we have to understand to go further into thermodynamics, and the second term is called thermal equilibrium, which we have to understand. So let us first understand this term thermodynamic equilibrium. So what I do here is I take a container with an ideal gas in it, and the walls of this container are very special. Walls of container are adiabatic walls. Adiabatic walls. What does this term adiabatic mean? So an adiabatic wall is one which does not allow energy in the form of heat to be exchanged between the system and the surroundings. An adiabatic wall does not allow thermal energy or energy in the form of heat, thermal energy, to be exchanged between the system. What is our system here? The gas. Between the system and surroundings. Surroundings is everything else except the container. So neither thermal energy can come inside this wall into the gas, this is not possible, nor thermal energy can go from the gas to outside surroundings, that is also not possible. So adiabatic wall is very special, a wall which does not allow the exchange of thermal energy on both sides is called an adiabatic wall. For example, if I have a wall and if I say this is adiabatic wall, then neither can thermal energy go from left side of the wall to right side, like this it cannot come, nor it can go from right side to left side. So the thermal energy is not allowed to exchange by an adiabatic wall. In contrast, the opposite of adiabatic is what is called diathermal. So diathermal wall or a diathermal container is opposite of adiabatic. Diathermal allows free exchange of thermal energy on both sides. For example, metals, most of the metals are good diathermals. For example, if I have a metal wall, for example an aluminium wall, then if on the left of the wall there is a substance which is giving thermal energy, that can pass through this aluminum wall and reach the right side. Okay, suppose if you are standing on the right side of the wall, you can feel this flow of thermal energy from a hot substance to you. For example, you go near your motorcycle. Some of the motorcycles nowadays have got this aluminum engine. So the inside of the engine there is petrol which is burning at a very high temperature, and when you go near the engine you can feel that thermal energy coming from the engine. So basically that metal is allowing that heat energy to come from inside of that engine to outside. You can feel that. So that is diathermal. So here what we are doing, we are taking a ideal gas in an adiabatic container. Okay, a container which does not allow thermal energy to be exchanged. Opposite of adiabatic is diathermal, which will allow exchange of thermal energy. Metals generally are very good diathermals. So we take this ideal gas in adiabatic container. So this is ideal gas, this is adiabatic container, and let us say I measure the state of the gas in this container. I measure the state of gas in this container. What is meant by state of a gas? State refers to the state variables which are generally pressure, volume, temperature, etc. Many more are there. You can have internal energy, entropy and all that, which we will study later. So state of a gas refers to the state variables or the values that these variables are taking. So when I say I measure the state of the gas in a container, for our reasons, for our simplicity, we can say I am measuring the pressure of the gas, I am measuring the volume of the gas, and I am measuring the temperature of the gas. Even though I am using the word temperature here, let us say we have not understood it thoroughly. Later I will introduce you to the concept of temperature in more detailed way. But right now I am measuring the state of the gas, means I am measuring all the properties of the gas, like the pressure, the volume, the temperature, and many other properties are there which we will study as we go along into thermodynamics. So I have this adiabatic container with ideal gas. I measure the state of the gas right now. After some time I again measure the state of the gas. After some more time I again measure the state of the gas, and if I find that the state of the gas is not changing, if I find that the state of the gas is not changing, which means the pressure is not changing, the volume is not changing, the temperature is not changing, and many other things are not changing, then I say the gas is in thermodynamic equilibrium. So when do we say a gas is in thermodynamic equilibrium? First, it should be in an adiabatic container. Very important. Why? Because the container is not adiabatic. Outside thermal energy can come and change the state. I don't want that first to happen. So I want the gas to be in an adiabatic container. After that, I start measuring the pressure, volume, temperature every moment. If it is not changing, then the gas is said to be in thermodynamic equilibrium. So thermodynamic equilibrium. See, the word equilibrium generally refers to a case where something is constant. For example, in mechanics, a body is in translational equilibrium, means acceleration is zero or velocity is constant, and a body is in a rotational equilibrium, means angular acceleration is zero or omega is constant. Okay, when you say body is in translational equilibrium, net force is zero or acceleration is zero, velocity could be constant, it could be zero or it could be some constant value also, depending on your inertial frame. Similarly, if a body is in rotational equilibrium, alpha is zero or omega is constant. So generally equilibrium refers to something being a constant. It's possible. Here in thermodynamic equilibrium, these state variables, which are pressure, volume and temperature, they are constants, they do not change, and many other variables are there which do not change, but mainly these three, let us say PVT. So that is thermodynamic equilibrium. So condition for thermodynamic equilibrium is a gas must first be in an adiabatic container and its state variables should maintain their values, they should not change. That is the condition for thermodynamic equilibrium. Is there a case where a gas is not in thermodynamic equilibrium? Let us look at one example. Suppose I have a container and I have a partition which you can pull it out if you want. Okay, this is a wall which you can pull out, and this side I have gas, let us say, and this side I have vacuum, and this is an adiabatic container, and this is an adiabatic container. Okay, now originally there was gas in the left chamber and right chamber was vacuum, and I suddenly remove this partition. Just after removing the partition, immediately after removing the partition, I measure the pressure, volume and temperature. So I remove partition. Just after removing partition, just after removing, I measure the pressure, volume and temperature of the gas. Then after some time, let us say 3 hours, I again measure the pressure, volume and temperature. Do you find any difference or not? You will find difference, because just after removing the partition, the gas is now about to expand. So its volume is still only 1/2. It is ready to expand. If I say this volume is V by 2 and V by 2, just after removing the partition, very instant when you remove the partition, gas is having volume V by 2. Soon what will happen? The molecules will jump to the vacuum side. Okay, and they will be going in very weird directions. After a lot of time, the gas would be occupying the complete container. So just after removing partition, gas volume is V by 2. Long time after removing partition, gas volume is V. Similarly, the pressure is also going to change. The pressure is also going to change. And temperature, we are going to see it later, that temperature will change in between, but finally it comes to same temperature. We will see that later. Okay. So the thing is, here the gas is not in thermodynamic equilibrium after removing the partition. Why? After removing the partition, if you start measuring the pressure and volume, they are changing, and temperature, they are changing. Okay, from time to time they are changing. Finally they get stabilized. Finally. So during this process of gas volume being changing and temperature being changing, gas is not in thermodynamic equilibrium. Long time after removing the partition, when everything is stabilized, then you can say gas is in thermodynamic equilibrium. So for a gas to be in thermodynamic equilibrium, A, it should be in an adiabatic container, and B, the state should not change. State means the state variables. This pressure, volume and temperature, these are called state variables, or you can say they are thermodynamic variables. You can call them as thermodynamic variables. So these thermodynamic variables should not change their values. So if the gas is in adiabatic container, and if the thermodynamic variables are not changing, then we say gas is in thermodynamic equilibrium. On the other hand, if gas is in adiabatic container but the state is changing for some reason, then it is not in thermodynamic equilibrium. You wait for some time, maybe the gas will settle and it will come to thermodynamic equilibrium. Okay, so this is the idea of thermodynamic equilibrium. Now with this idea, let us go into thermal equilibrium, the concept of thermal equilibrium. Let us look at thermal equilibrium. In fact, thermal equilibrium will lead us to the concept of a new quantity, which is temperature. Even though you have studied about temperature, I suggest you forget that you have not encountered the word temperature at all. Let us say, up till now you have not even once heard the word temperature. For the first time, we will understand from where this word called temperature is taking birth. So let us look at thermal equilibrium. When you talk about thermal equilibrium, you must take two systems of gas. So there is an adiabatic container, let us say container 1 with ideal gas 1. This is one system, and there is another system, adiabatic container 2 with another ideal gas 2, and both these were originally in thermodynamic equilibrium. So this was also in thermodynamic equilibrium. This was also in thermodynamic equilibrium. This is also in thermodynamic equilibrium. This is also in thermodynamic equilibrium. That means for both these gases, the state variables are more or less stabilized with constant values. Okay, we have two such gas containers. Now suppose I bring both these containers and make them touch each other like this. Of course here the adiabatic walls are touching. These are adiabatic walls. The bold line that I have shown, that is the adiabatic walls of both the containers which are touching. So this is ideal gas 1 and this is, let us say, ideal gas 2. So these two containers are touching. Now somehow magically I will change these walls from adiabatic to diathermal. How I will do it, that is not important for us right now, but somehow I change this. I change this partition, which is actually two walls which are touching, this partition from adiabatic to diathermal. Okay, so after changing it from adiabatic to diathermal, I will start measuring the state of this gas and also this gas. Suppose if state of both gases is still not changing, okay, the ideal gas 1's state was what it was originally and ideal gas 2 state also is what it was originally, even after replacing the common wall, the common partition from adiabatic to diathermal, then we say these two gases are in thermal equilibrium. So when you talk about thermal equilibrium, you are talking of thermal equilibrium of two systems. There must be two systems and only then you can say they are in thermal equilibrium or not in thermal equilibrium. Whereas when you are talking about thermodynamic equilibrium, you are talking about a single system in adiabatic container. Here there are two systems which are in contact by a diathermal wall. Okay, so two systems when brought in contact with a diathermal wall, if they do not change state, they are said to be in thermal equilibrium with each other. Now think for a minute, what does a diathermal wall do? If you replace this with a diathermal wall, if you replace the adiabatic with diathermal, the only difference is it will allow the thermal energy to flow either from left to right or right to left. But state is not changing. When will state change? When thermal energy comes, pressure may increase, temperature may increase, state will change. So thermal energy is not flowing even after replacing them with diathermal wall. When does that happen? When something is same for these two containers, then there is no thermal energy exchange. That something has been named as temperature. It is a scalar. So when two systems are in thermal equilibrium, there is something that is same for both the systems. There is a scalar quantity that is same for both the systems. That scalar quantity has been called temperature. So the birth of temperature is coming from this idea of thermal equilibrium. Okay, once again, please listen to this carefully. First, to discuss thermal equilibrium, there must be two systems. Okay, both of them actually were in adiabatic containers and both were originally in thermodynamic equilibrium. So both state originally was constant. Now you bring them in contact with a diathermal wall. After bringing them in contact with the diathermal wall, even after that, if state is not changing for both systems, we say they are in thermal equilibrium. That means something is same for both. That something we are calling as temperature. So I can write now, two systems are in thermal equilibrium if their temperatures are same. If their temperatures are same, thermal energy will not be exchanged. In fact, in practice it has been found, when will thermal energy be exchanged? When temperatures are different, definitely thermal energy will be exchanged. Put two objects at different temperatures, The one at higher temperature will give thermal energy to the one at lower temperature. Okay, energy in the form of heat will be exchanged. But if temperatures are same, then there is no way naturally this thermal energy will be exchanged by both these objects. Okay, you can force it, that's a different issue. But naturally thermal energy will not be exchanged. You can force it. For example, you keep something in a refrigerator and you force heat from that to outside. You force by doing certain thing. But naturally thermal energy will not be exchanged by two objects at same temperature, right? So the concept of thermal equilibrium results in what is called temperature. So I can say if two systems which were originally in thermodynamic equilibrium, which were originally in thermodynamic equilibrium are also in thermal equilibrium, then there exists a scalar called temperature which is same for both systems. Then there exists a scalar called temperature. So first time I am introducing the word temperature to you in a very clear way. There exists a scalar called temperature which is same for both systems. So I can say now if two systems are in thermal equilibrium, then their temperatures are same. Even the reverse statement is correct. If their temperatures are same, they are in thermal equilibrium. So let's write this. If two systems are in thermal equilibrium, then their temperatures are same. The vice versa is also correct. So I can write if and only if two systems are in equilibrium, if and only if their temperatures are same. If and only if means the reverse also is correct. If their temperatures are same, the systems are in thermal equilibrium. If two systems have same temperature, if two systems have same temperature, then they are in thermal equilibrium. Okay, so this is the whole discussion about thermodynamic and thermal equilibrium. In fact, this statement which I just gave now, which statement? If two systems are in thermal equilibrium, then there exists a scalar called temperature which is same for both. This statement is called zeroth law of thermodynamics. This is called zeroth law of thermodynamics. Of course, generally the textbooks quote a different statement. Both are same. What the textbooks quote is, if two systems are in thermal equilibrium with third system, then they are in thermal equilibrium with each other. Then they are in thermal equilibrium with each other. This is the generally quoted statement for zeroth law of thermodynamics. Suppose I have system A, I have system B. System A is in thermodynamic equilibrium with system C. What could be system C? Later I will tell you. This is a thermometer which can measure temperature actually. Let us say thermometer. It can be anything, but I will call it a thermometer. Nothing wrong. So A is in thermal equilibrium with system C. Okay, that means both these temperatures are same. B also is in thermal equilibrium with temperature with system C. It's both these temperatures are same. Means A and B temperatures are same. They are in thermal equilibrium with each other. That means if these systems are in thermal equilibrium, there exists a scalar which you can measure with a device called thermometer. There exists a scalar called temperature which is same for both the systems. It's an indirect way of saying. So both these are zeroth law of thermodynamics statements. Okay. So you can say if two systems are in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Or zeroth law can be said like this: if two systems are in thermal equilibrium with each other, there exists a scalar called temperature, which you are measuring with a third system called thermometer, basically, which is same for both. Okay, so either way it is the same statement. If you think about it more deeply, both the statements are similar. Okay, this third system can be anything, but I can take it to be thermometer basically. So system A, and if thermometer are in equilibrium, thermal equilibrium, thermometer will show some reading of mercury. If I put it to B, if it shows a different reading, then they are not in thermal equilibrium. But if it shows same reading, then B and C are also in thermal equilibrium. Then A and B must be in thermal equilibrium. So if A and C are in thermal equilibrium, if B and C are in thermal equilibrium, then A and B must be in thermal equilibrium. This is zeroth law. Okay, so it's up to you. Why it is called zeroth law, by the way? Generally our numbering starts from first, second, third, fourth. But why is it called zeroth law? The problem is temperature is such a fundamental thing in thermodynamics that the definition of temperature was realized much later than first law of thermodynamics. So first law of thermodynamics was formulated first. Okay, then they found that temperature is more fundamental to first law. When you name something as first, and if you want to name something before first, so you have to go with zero. Zeroth law of thermodynamics. Okay, so zeroth law was discovered much later after first law. Okay, so that's why it was called zeroth. Suppose if you discover something more fundamental than zeroth law, you must name it as -1th law now. Okay, of course there is nothing more fundamental in this subject, but that is what is the nomenclature. Now from here you can deviate and go into what is called thermometry. One path is to go into thermometry from here, but that I will take up later. The other path is to go directly into thermodynamics from here. So that will be first we have to discuss specific heats for that, and then we can go into the other aspects of thermodynamics. So I am going to take that route from here. We will discuss this thermometry later. I will first go into thermodynamics. I will take you into the subject of thermodynamics from here. Okay, so that is what we are going to do in our next lecture.